and he did his PhD in Vienna in Bodenkultur University. And then he moved to Colombia, to University of Los Andes, to be an assistant professor there. And since September, you are?
August.
Since August, he's in Delft as assistant professor of experimental soil mechanics.
Yeah. Thank you, Amin. So good afternoon, everyone. Because since August I'm in Delft, I will not present you any work of Delft. I don't manage to be that fast. But I will show you a nice work that involves some of the aspects we have seen today. And it involves one that we as geotechnical engineers, we tend to discard. That is the effect that a couple of grains has on water. So after the nice videos, for example, of the experiments that Stefano showed us, that landslide went into water, and that impact generated a wave. So this work is thanks to the collaboration of many people, many nice students. So for example, Andrea Jara, Gustavo Pinzon, Oscar Polania, they were at that moment very good master students. And now they are PhD students. And they helped me a lot in developing this type of experiments. And then thanks to the collaborations with other colleagues like Nicolas Estrada in Los Andes and Ryan Mulligan and Andy Take in Queen's University in Canada, we were able to explore different aspects. So don't limit just to the landslide, but look a bit to what happens after that. So the topic I'm going to talk to you now is about landslide generated waves. And landslide generated waves are something, if you happen to go to a pool, you will know when you jump into the pool because you move water. And that displacement of water in a pool is not a serious matter. But if you are next to a glacier or next to a lake, it could become another story. So for example, here what I'm showing you is a video of a glacier calf that is basically a portion of the glacier tumbles and slides down, impacts the water, it displaces a lot of water, and the people that is recording this video is on a boat. And they're happy because they're seeing something quite unique until they feel the wave quite close. So the velocity of the wave is impressive, and it can be up to several couple meters. So it is something that can interact with coastal infrastructure, with offshore infrastructure. And for example, it also involves other types of landslides. This that I'm showing you here is the Anak Krakatau volcano eruption. And you will guess that's not at all the slope that we need to worry in geotechnical engineering. But I will disagree with that. Volcanoes have different ways to erupt. And one of the ways it has to erupt is that one flank of the mountain will slide down. And that mechanism is exactly what we do in geotechnics. Is the material reaches a shear strength. Usually in volcanoes, because of the temperature, you have effects of hydrothermal alteration of the rock. And that hydrothermal alteration fractures the rock and leads the whole mountain to behave as a soil. With the characteristic that this volcano that was in an island, part of it was immersed and part of it was on air. So when you were going to think what will happen if that landslide occurs, you certainly would expect that it will push water sideways. But in order to predict how much water it will push, that's another story. The tsunami that was generated in this volcanic eruption caused a bit more than 220 deaths and reached the parts of Sumatra and Java. So it really became a serious matter. And if we think of these type of landslides, you can also guess that those you can find them in several areas in the coast, just that probably we are not that aware because only people live in this coast, but they certainly will interact with several infrastructures. So there are two main mechanisms to try to idealize what is the momentum transfer from a landslide moving and impacting a water reservoir. One option you have is the fun moment at the pool. You jump in, and as a function of the velocity and your weight and your cross-section area, that's a weird way to call a person, but if you accept that, you will displace a volume of water. And the amount of volume you displace will propagate in all directions equally, and eventually will reach the borders and reflect and so on. But that initial wave is what matters the most. That is usually called a solitary wave. But there is another option, and is this second case, when you are fully immersed in the water. So when you're fully immersed, you can really tell that water is doing something to you. You cannot run as fast as you were running on air. And that is basically because of drag. So when you have a submarine landslide that half of it is underwater and half of it is on air, it becomes difficult to guess what will be the continuity equation for momentum, because part of it will be moving very fast and part of it will be moving very slow. But at the moment the fast part is moving into water, it turns rapidly to a slow motion. And everything is happening while the soil is deforming because it has a permeability, and while the water is being displaced. So not a simple scenario at all. So for that comes physical modeling, to make a complex process a bit more simple. Several experiments have done in the past, for example, these ones that were done in Queens, and they took the Canadian way. They took a ice hockey ring, they put a slope on it, and let a bunch of material to fall onto a water reservoir. The impact of that flow, of that granular flow, then generated a wave, and they started to change several aspects. They looked, what if the thickness of the flow is larger? Will I expect to have a larger wave? What happens if I saturate these grains? Will they then displace more water because water will not penetrate into the grains? And they came out with this very simple equation. This equation is just the AM is the amplitude of the wave, of the generated wave. You have rho S, which is the density of the soil, S, the thickness of the soil, Vs is the velocity of the landslide, alpha is the inclination of the slope, and rho is the bulk density, and gravity times the height of the water reservoir. So with this very simple equation, they were able to tell what should be you expect when a landslide impacts a water reservoir. But that was not enough, because part of it cannot be submerged, therefore will not generate a wave. So other group started coincidentally at the same year to show a different type of mechanism in a physical model. In this case, they had a granular wedge that was fully submerged, and I want you to pay attention to that panel B on the top right. You see that there is a deformation on the surface water. The deformation happens because once the wedge is released, it drags water down, and the drag of that water down generates a depression on the water surface. And we know water has no shear resistance, or at least very low. So that depression is rapidly filled, but by filling that depression, you generate a wave. So a submarine landslide can also generate waves. And then you come to this condition that is more common to us. You probably have heard in your geotechnical books about the landslide of Bayonne. That landslide cannot be more famous, like really. There have been so many things. And still, they managed to publish new things. This is not Bayonne, just because Bayonne, you have seen it many times. But this is a very similar case. This is a landslide that had a toe that was immersed on a lake, and part of it was on air. This was in Alaska, so not many people was worried that that landslide could generate an issue. But in Alaska, nowadays, there is pipelines, and there is all sorts of infrastructure that is unattended and left there because it's Alaska. What happened here was that the landslide displaced a lot of water from the lake and generated a tsunami wave that then saturated the banks of the rivers, generated more landslides, and that turned out to be a serious flow. And when we started looking at this problem, eventually we came out with this idealization. And is that if you normalize again, AM is the amplitude of the wave you generate, and you normalize it by the thickness that is immersed in water, and you compare it with the thickness immersed in water with the total height of the landslide, you have this very continuous transition from something that is fully submerged, meaning that the height of the landslide is below the height of the water table or the water level. And you see that at that point, you have a transition from subaerial landslides towards submerged landslides. So basically what we were trying to aim here was, would it be possible to have a marriage between what you have as subaerial landslides impacting water and fully immersed landslides displacing water? Is that possible? So with that question, we came with this publication that then transformed into, is there a relationship between the generated wave amplitude and the submergence level? The submergence level is another way to say how much of my total height of the landslide is immersed. Is it above the total height of the landslide or is it in the middle? If it is nothing, there is no water to displace, so no wave. So it usually should be higher than 0. So for that, I'm going to present you a physical modeling approach that does not use centrifuge, does not use large scale, does not use field scale neither, but is useful because physical modeling is meant to be useful. And that use needs to be, for example, Luke was showing yesterday the wind turbine of Gustav Eiffel. The scaling factors are what help us idealize processes. We don't do experiments just because they're complicated. It's because we want to get an easy answer. And that was the motivation we keep on this campaign of experiments. So the question was, what controls the mobility of a mass movement, of a landslide? So not what is the sliding plane, what happens afterwards? How far will that landslide go? And then please remember this, all models are wrong, but some are useful. So if you believe in that, then everything is wrong, but some things might be useful. You might accept this simplification. A mountain, it consists of a slope. You usually have gravity on Earth. It's difficult to avoid it. You have a series of vegetation. You have rain, weather, so on. You have animals. Inside the soil, now Stefano told us we have plenty of roots. And by the combination of all these, you have a sliding plane. And that sliding plane might be curved, might be a straight line, whatever it is. It is something that separates something that is not moving with something that moved. I want you to accept that that is equivalent to this block. It's a difficult to accept this because, come on, we're geotechnical engineers. We need our slope. If we don't have a slope, what type of stability can we do? But bear with me, and let's accept that the simplification of this problem can be a box or a square that will show eventually a failure plane, and that failure plane will remain the same because it's a frictional material, or it can have some cohesion, but the failure plane does not change because of the geometry of the problem, it's just because of the material. Therefore, if you change the geometry of the problem, you're just changing how much mass it will displace. And this is basically an experiment that was designed by the physicists. And they came out with these models in 2004. So these videos are when they managed to make nicer videos. And the principle is very simple. Instead of doing what we as geotechnical engineers did in the last 50 years, that was doing slopes, these guys went right to filling a glass with sand, putting top down, and lifting up very quick. Therefore, you have a granular flow. This granular flow shares many similarities with landslides because, again, it has a failure plane that separates something that remains steady with something that moves. It has a series of velocities on that range where the particles that are on the surface move faster than the particles that are near the failure surface. And all that allows to explain from a very simplistic way how far a landslide would go. Based on that, people have managed to make these two types of measurements to relate the initial geometry of the column, is called a granular column collapse, so the red rectangle, and relate it with the final geometry of the deposit, here this cyan triangle. Based on those two, what you have in the vertical axis is the final distance of runout versus the initial thickness of the column. And on the bottom, you have the aspect ratio, which is just the ratio of how high versus how width it was. Okay? Based on that, you can have two possible scenarios. Your sliding plane will cover the whole column, and you end up having a triangle, or your sliding plane just cover a wedge of it, and you have a plateau on top of the deposit. This distinction is what is being told to be a short and a tall column. A short column, only a portion of the volume detaches. A tall column, all the volume that is possible to move on the sliding plane will move. And you relate what you find from short and tall columns with the runout distance. And therefore, if you now look at the landslide and you get an idea of what the volume of that landslide is, you might give an order of magnitude prediction of how far it will go. So for that, we built an experimental model that is inspired by, is anyone from Czech Republic here? So I remember going to Czech Republic and looking at this shadow theater. Have you heard of that? Where you project a light, you backlight a puppet, and you can see the movements from the shadow, and just the interpretation of your eyes of those movements tells you very precisely how the toy is moving, and your imagination does the rest. So here we do exactly the same. We add a LED panel that backlights a series of particles that are placed on this bottom right corner where the XYZ axis is. And you record on the other side with a high-speed camera. The recordings look something like this. So what you see here is each single particle moving, because this model is just one particle thick. There is no particle behind each other. And this is something that is very neat, because you can then use PIV, PTV, whatever image analysis you want, and you can tell exactly how fast particles move. You can also tell whether or not some regions dilate or some regions contract during the movement. And that, again, is an oversimplification, but it's an useful one, because we can tell what happens during a landslide. And now that you see, let me go back. Usually these column collapses initiate as a sudden vertical movement. That vertical movement transitions towards a lateral movement, and now you have a really shallow layer of particles moving, and that shallow layer remains with a constant thickness. Particles are jumping around, doing whatever they want, until eventually they reach a deposit. And in this case, the deposit has the shape of a triangle because it's a tall column. So basically what we did to study landslide generated waves was to add some water, and look what happened. So we added some water just by adding a little pipe on the side, filling in the gap. And here we had to be quite aware of the potential surface tension of water. Because if a dry particle, a collection of dry particles jump into water, surface tension might generate a capillary bridge that generates a bubble inside the soil. And that is somehow annoying because it dissipates momentum transfer. So there was a very easy trick to do here, and that one was to add a bit of soap. And soap reduces the surface tension of water. That's why we can wash our hands. And then you have these beautiful immersed landslides. Let me play it again, because here goes a principle that is, if you look at cyclism, you will notice that in a cyclism, you have a team, and the drivers that go on the front eventually go back. Here you have exactly the same. You will see that some clusters of particles start to appear on the front, and they are moving back. And that's because they receive most of the drag, and by receiving the drag, they let the particles that are behind to move ahead. And overall, the collapse is slightly different to what we have seen before that was dry. Here, still we have a vertical motion, but that vertical motion rapidly transitions into a lateral motion. And that lateral motion is only possible due to dilation. Please notice that there is a wedge where all the particles you'll see more white spaces between the particles. And once they are moving, they reach this critical void ratio that we like in soil mechanics, and they come into an almost steady motion. We happened to have fun. This was the art of Gustavo. He took a kid's book on how to see motion in fluids. And with a very precise combination of milk and alcohol, you can get the same density of water. So all these stains you see here is a tracer for the fluid. And what I want to catch your attention here is that once the landslide happens, it's dragging water from the top that moves towards the left. That water is being continuously dragged. And eventually when the landslide is reaching its deposit, it starts to expel water. Please note to the front of the landslide, that white region that is appearing. That is water that is pushed away from the landslide. And this later on, we managed to have a project with the oil company in Colombia. And they were wondering what will be the impact of a submarine landslide against an infrastructure, an offshore infrastructure. And we came out with the answer that it is not only the landslide that you should be aware of, but also the water that is expelled out of the landslide. So now going back to landslide generated waves, here what you see, we added a little dye just to have a sharper distinction between the water surface and the landslide. And you notice that a depression was caused. Let me put it back. Please note that just above the edge of the column, a depression generated, and that makes a wave that is moving towards the left. If you think of this as a coastal engineer, Ryan Mulligan is a coastal engineer. He told us that is beautiful because that are called coastwards waves. And those are the ones you're more worried if a landslide happens near a beach. Because a submarine landslide propagates far from the beach, no one cares. It's just boats there. But if the wave goes towards the coast, there is a lot of issue. But these are the waves we're more used to. So you have a landslide, and that landslide is impacting the water and generates our wave. Please note this area that is dry right at the bottom of the column. That dry area is just showing this beautiful competition between permeability and the motion of the grains. Permeability is trying to get into the granular material. The permeability here is very low, but the grains are moving faster than permeability. Therefore, the grains cannot be saturated just until they are stopping. Let's put it again. So please note how the dry pocket appears there, and it's not about surface tension. It's just because particles are moving faster. And that gives us an idea that the momentum transfer in a granular material should be higher than just accounting for a relationship between permeability and the velocity of the landslide. So with all these beautiful experiments, what we came out was with a collection of observations that were based basically on image analysis. And here I want you to catch your attention that image analysis is not just PIV. Image analysis is everything you see with your eyes can be transferred into a computer vision analysis. For example, a very simple analysis you can do is to tell where water is and where is not. That is called a segmentation. And with that segmentation, you have a clear idea what is the shape of the water surface in the whole process. You can do as well PIV. That is what is shown in this column C. And PIV will tell you what is the shape of the wedge that was pushing the water and where do you expect to have the higher velocities. But there is another image analysis technique that I really like because of its simplicity. And this is called an spatiotemporal analysis. In an spatiotemporal analysis, what you will have is something that looks very much like the photo finish you see in the Olympics. Did you notice something weird in this photo finish? These people are athletes, so they are deformed, but not that deformed as they are shown in this image. What do you notice is weird on there? The one on the top right. Do you notice something with their feet? Are they of the same size? Are there natural feet? Some of them. But then why? These are athletes again. They run very fast. How do they manage to be so deformed in this picture? So the spatiotemporal analysis, or the cameras they use for the Olympics, are not the regular cameras we have with the sensor that goes like a matrix. It doesn't go X pixels wide, X pixels high. They only take one line of pixels. And they take that line of pixels over the finish line. That's why the background is white. If you recall from the Olympics, the track usually has a color, blue, green, or orange. But they place that line of pixels right at the finish line. And by placing it right at the finish line, what you see in the x-axis is the time. So the athlete that is more towards the right is the first one that arrived to the finish line. And then you move towards the left to take account for the time. And therefore, you have a direct measurement of time here, because you have time on the x-axis, and on the y-axis, you have a space. So basically, what we do is exactly the same. We take a line of pixels in the vertical direction, and we plot that line of pixels against time. Here comes the beauty of this technique, is that if you measure a slope, that slope is delta space, delta length over delta time, which we like to call velocity. So you have a direct measurement of velocity with a strong precision, and has nothing to do with a cross-correlation algorithm. It's what your eyes see. So that's why I really like it. Also, it allows you to have direct measurements, again, with a very nice precision of the wave amplitude. And if you perform this space-time analysis along the image, you will certainly find out where the peak amplitude of the wave is, what is the velocity at which it's moving sideways, and all the characteristics of that. So with that in mind, we came out to this that I already anticipated, the mechanism making seaward waves and the mechanism making seaward and landward waves. Landward was the appropriate term. So those two kind of waves are relatively different, but they encompass the same mechanics. Part of it is immersed and part of it is in air, or might not. But eventually, in both cases, they are displacing water, and the displacement of this water has something to do with the dilation of the landslide and the velocity at which it moves. So you can have different analyses, like what is the wave amplitude of those seaward waves in time, and you see that it dampens with time. There is one instant when the wave reaches a peak, and then it dissipates. That is very common in solitary waves. And when you have a landward wave, you get something similar. So we started mapping what was the amplitude of those seaward and landward waves as a function of the submergence ratio. Again, HW over H0 is just how high was the water table or the water surface relative to the height of the column. And somehow we see that there is a continuous. So there should be a mechanism here that could allow us to tell or to predict what is the wave amplitude. So we came with a mechanism, and I wanted to show it to you. This mechanism, the mechanism, is very simple. And if something is simple, might be wrong, but might be useful. So what we took was the instant where the wave was the highest, okay? Just that instant. And by looking at the instant where the wave was highest, we tried to look at the slope of the landslide. Please notice that those cases of low submergence ratio, the ones on the left, they are the ones that are with a lower slope. But as soon as the submergence ratio increases, the slope becomes steeper. So there must be something there. So what we came out was to say that slope is telling us something. Why not to explain that the slope of this instant is a function of the submergence ratio. And by saying that, we will imagine that there is a wedge that is either pushing the water sideways or pushing the water downwards. And that pushing is equivalent. It doesn't change so far for our experiment. So we just want to know the geometry of that wedge. And there is a way to get the geometry of that wedge. And is if you take the momentum balance of a granular material that is pushing a water reservoir and initially still water, you get to these two momentum terms. You have the momentum wedge, the momentum term for the solid wedge that is just a function of the grains density gravity and this length, the horizontal length of the wedge. And you have the momentum transfer to the water that is just a function of the water thickness and the wave, but we don't know the wave. We will figure out later. What we need to assume is that the momentum transfer from the solids is transferred to the fluid fully. There is no dissipation. And that might be a strong assumption, but for the sake of simplicity, let's assume there is no dissipation. So momentum of the solid wave equals the momentum of the fluid wave, and therefore we came to this equation 3. This is a second order equation. We like those because we can find the roots. And the positive root, which tells us what is the positive wave amplitude, looks something like this. In this case, we are only left with one unknown. What is this length L? And there is a way, here comes the second assumption, and is that this length L has something to do with the center of mass of the column. But this center of mass needs to be the compound center of mass. It's the center of mass of the granular column and the center of mass of the water table or the water level. And we want to make things more simple even. And we don't want to matter of the center of mass in the horizontal direction. We just want to know the center of mass in the vertical direction. Therefore, the middle height of the column and the middle height of the free surface water. And by doing that, we get this letter C in equation 6. And by knowing C, we know L, and therefore we might be able to know the wave amplitude just by knowing the geometry of our problem at the beginning. If we plot all the data points we collected in this experimental series, they fall in this trend. That is very continuous, very nice. But we received some comments. The experiments were just 45 centimeters wide. And the comments we received was like, come on, landslides are larger. There is for sure surface tension there. Your experiments are just too small. But all experiments are wrong, but some are useful. And we said size does not matter. So we took other people's experiments and plot them over our experimental data. And these experiments are of meter size. So they are relatively large and they were accepted to be okay. So if their observations are okay and coincide in this representation with ours, we can assume ours are also okay. And out to our surprise, then we came out to this realization that if we take the equation I just showed you and we plot it here, we should expect an agreement. Our surprise was that the agreement was very good. So the red line is showing you directly the prediction from the simple equation. And the lighter band around that is just a 5% error, because, come on, it's a simplification. And again, the only model parameters you need here are very simple. So what we came out with this was to a way to allow a first order prediction of the wave amplitude if you happen to know the geometry of your problem. So you might do a slope stability analysis and know what will be the whole height of your slide. You know what will be the water level conditions. And if you know something about density of water, doesn't change that much. Density of the soil doesn't change that much. You have enough ingredients to predict what will be the wave that generates that landslide. And interestingly, it follows a similar trend. So just coming to the end of the presentation, we can say that there exists a transition between subaerial and submarine landslide generated waves. This transition can be expressed as a function of a continuous momentum flux function. And this simple model might be wrong, but it's useful and can be used in tsunami hazard assessments. So just to give you an idea of other works we've been doing, we started changing the grain shape. So by changing the grain shape, we were interested in knowing what happens if you have an interlocking between grains and how grains move in a fluid. So you have this fluttering effect, like a leaf falling off a tree that does this. And that same mechanism happens here just for those grains that are isolated. But when they are collected or they're moving as a collection of grains, it no longer happens. And this was the thesis of a student that is now in Barcelona. She became very happy with this idea and started using the stars. I don't know if it might be useful, but it's fun. Then there were these other experiments that were done at Queens with transparent soils. And here the idea was to explore how the desaturation occurs in a landslide once you release it. So the instant you start to see in white is because air got there. And we were trying to compare what is the difference between the column collapse of a dense material and a loose material. And in a dense material, we expect dilation to happen. That is obvious. But what was new here is that we saw that dilation happens as a series of fingers that penetrate just to a certain thickness and destabilizes the whole column. And finally, I added just this one because of the nice experiments that Yanis showed us yesterday. This is just an impact of an permeable obstacle. And what you have here is something that might be wrong, but might become useful, because it tells you that water is percolating on the permeable obstacle. And what you see on the bottom, these eyelashes are analog displacement sensors. You can tell when the moment they move down is because there is some weight. And if they move back up, the weight has been released. Therefore, they work as a load cell, just that is analog. And you can do all that with image analysis. And what we were working here was what was the impact of a fluid on a gabion, and what should be the dimensions of a gabion to remain stable. So with that, I finish. I thank you for your attention. And again, I would like to thank the students and the colleagues that helps this research to happen. Thank you.
Thank you, Miguel. Are there any questions? Was it?
Thank you very much, Miguel, for this impressive work. My question is, the angle of the grains after the slide has any relation with the friction angle at repose, or?
Not this angle, but the angle of the failure plane. The one that is
at the end of the slide when
the one of the deposit.
Yeah.
Yes, that is basically the repose angle of the material.
But my question is that perhaps I have misunderstood you, or I have lost something. I see that there is a difference when you make the experiments with water and without water. I think that angle is not.
It is different. Yeah, and it is different not because of, let's say, it's not a material property there, but it's an interaction. So the reason why in a dry flow the grains reach that far, or they reach farther, is because the bottom surface is relatively with a low friction. And therefore they can spread as long as possible, but eventually they stop. And they stop because of friction against the walls or against the base plate. In a fluid, the same boundary conditions appear, but in a fluid, you have the additional effect of the water slowing them down. And because of that loss of kinematic energy, is that they don't manage to reach that far. So in this configuration, the slope you reach is not in an immerse experiment, is not the repose angle, but it's just because of that interaction with the fluid. Thank you.
Maybe I ask a question as a follow-up. So here, when you showed the top view of your experiment, I think it's a rather narrow one, right?
Yeah.
So looking at it that it's a 1G experiment, how much is the effect of the side boundaries, so the lateral boundaries?
So these are ceramic beads, and the two transparent windows are plexiglass. And the friction coefficient, we measure it, and is 0.05. So there is friction, certainly. But because these two walls are separated to 1.2 times the diameter of the spheres, and the spheres we bought are meant to be very precise, so the diameter has less standard deviation than this 1.2. So one particle will only be in contact with one wall, not with the two of them. Therefore, the friction effect might be lower. And we assume that that is a second order effect. But certainly there is something, but this is brought to the extreme that it is there, but is not playing a significant role. What we see is the frictional, mainly controlled by the friction between the grains contacts and how they jump between each other.
Other questions?
Okay.
Seems to be not
Yeah.
the case. Thanks a lot.
Thank you.
Miguel.